Very good. Hi, everybody. So I assume everyone's working away on their homework. Manuel has graded the first assignment. I just haven't looked at it yet. I'll return it to you next week. All right, very good. So last time we were talking about nonlinear optics as a precursor, as a way in which we will talk about the generation of non-classical light, in particular at the moment, squeezed states of light. Okay, and so the specific example, the simplest nonlinear example we have is what's called three-wave mixing, where we have this chi-2 nonlinear optical crystal, and there are three waves that mix, hence the name. And the particular processes that are resonant and that will amplify are the ones that satisfy the so-called phase matching conditions. So the three waves are chosen and aligned here, is chosen within the crystal, such that for three frequencies, omega 1 and omega 2 add up to omega 3, and the wave vectors add up. Okay? Then we say that the process is phase matched. This is just what is a requirement for us to stay resonant. And this process had to do with where we said as the polarization was oscillating and propagating, that would stay in phase with the pump, and then we can get a strong conversion. Okay, that's where the term phase matching comes from. Right, so Maxwell's equations gave us a set of coupled nonlinear ODEs for the three waves as it propagates along the direction of the crystal. Okay, and in particular, so these are these three coupled differential equations. We can't solve them exactly. They're nonlinear. But we can solve them under some approximate cases. And the specific example we're going to look at, let's say an example of what's known as an OPA, or an optical parametric amplifier. So the idea here is that we'll take one of these waves, say this one, the one at the high frequency, it might be ultraviolet laser, say, that we're going to have a good, strong intensity on. And then we might want to then, say, amplify this other wave through this nonlinear process, parametrically amplify it. Like you're studying a parametric amplifier, just so you know, a bob on a string in your homework. It's the same exact process. And so, you know, we might say this will be our signal that we want to amplify. And say we inject some small amount of intensity into the crystal at some direction, then we get an equations of motion. We treat this as a constant, and we just set this equal to 0, and this amplitude we take to be constant. And then, so we take this to be constant, whatever related to the incident intensity in phase of that pump. And then we get a coupled of linear ODEs for the two modes, which we call the signal and the idler. Okay? And these equations we recognize as the same kind of equations of motion that you see in your homework. Say in the Heisenberg picture as a function of time, this is as a function of propagation distance. In this case, the propagation distance plays the role of time in this Fourier domain. But the bottom line of this is that we see these differential equations that we're familiar with now as the equations that generate a Bogoliubov transformation. Okay? In this case, it's a two-mode Bogoliubov transformation because we have these two modes. These two modes that are the ones that are being coupled together. And what we see here is that we get an amplification of the signal. Even if so, if we said we put nothing in the input on the either, we could just neglect those two terms. If we injected no light at the either mode, then we would see that we would amplify the signal, and simultaneously we would generate a second conjugate beam, as we call it. That it's conjugate because it is growing like the conjugate, depends on the conjugate of the input phase. Okay? This is classical nonlinear optics. Okay? So just a couple more statements about this. Let's suppose, for example, we had the case of collinear one Allen collinear? Two, that's funny. Phase matching. We'll take to be degenerate. So let's just say that omega 1 equals omega 2 is half of omega 3. Okay, so let's just say we set up the crystal in such a way that we can satisfy those conditions. It depends on technical details of what the birefringent crystal is and how we do that, but who cares? At least I know right now. So under that situation, then the signal and the either are the same mode. Okay. Let's just call it E. Right? So then we have a one-mode Bogoliubov transformation under that situation. So that mode will evolve according to this equation. Right? And so what we see in this case is that what will this parametric amplifier do? This is a phase-sensitive amplifier. Right? Because the particular quadrature of the electric field, which is amplified, well, it depends on this theta, which depended on the phase of the pump, right? And this is the same thing you're solving in homework, right? Where you looked at the parametric amplifier, and you saw that certain quadratures are amplified and certain quadratures are de-amplified. So what we would say, let's say, just thinking about this from a classical perspective, we could say, let's look at a phase space diagram with the real and imaginary parts of this guy, which are the quadratures. Thought about it as a phasor plane. So there's some, we might have some initial input here at some whatever the phase is of this injected field relative to the pump. Okay, phase. And let's say that I had, you know, a statistical distribution. Well, let's look at one of these at a time. Okay, let's say that it were such the case that we chose the phase of the pump such that this direction the one with the quadrature phase equals 0 is amplified, and this quadrature is de-amplified. Okay? So what would be the phasor on the output? Well, this guy would grow by some amount, right? And this guy would shrink by some amount, which just would be, you know, either the kappa r along that direction, and then I would exponentially shrink by some amount along this direction. How much should I shrink that to be exponential? Over here? Okay, let's just say that. So the output would look like that, right? That would be an example of a phase-sensitive amplifier. This fraction of that quadrature is stretched and the other quadrature is de-amplified. Okay? Now suppose that I had some statistical distribution of, you know, let's just say classically, I don't know where that phasor is. I might say there's some distribution of possible initial phases. I don't know, it's just a random variable. Okay, classically statistical. What will happen? Well, each one of these guys will undergo its own exponential stretching, right? I can think about this as a bunch of different points. I can look at this particular point that's over here, and it will get, you know, stretched by some amount along here and stretched out the other way and end up over here, right? And so all of these points will end up somewhere in some other distribution, stretched out in one side and squeezed along the other one. Okay. And so it's clear from this that parametric amplification is associated with squeezing, because it's a phase-sensitive amplifier. Certain quadratures are stretched, anti-squeezed, and other quadratures are de-amplified, and this is squeezing. Okay. Now, how do we describe this from the quantum mechanical point of view? Well, from the quantum mechanical point of view, we have to write down the quantum expression for the electric fields, right? So, quantumly, what we have is some interaction Hamiltonian, which is minus P dot E, P meaning the polarization density, which is going to have the chi2, and then I'm going to have terms that look like this. So what have I done here? Well, I've written down my Hamiltonian, as minus the polarization density dotted into the electric field, right? And I'm saying I'm only going to keep the phase-matched terms because they're the only ones that are going to survive the scattering matrix. I have to satisfy energy conservation over here. And I'm going to choose things to also be phase-matched decay. And so there will always be two of the modes that, in order for this to be resonant, there will always be the case that two of the modes, the frequencies add to the third. And I'm calling one of them the pump, the big one, and the other the signal in the either. Okay? So this kind of Hamiltonian, and I'm very loosey-goosey here. I'm not going through all the derivation because I just want to get the essence of what's going on. Is going to be, you know, there's going to be some sum over all kinds of stuff, and there's going to be things that involve creation-annihilation operators associated with these modes. Right? The positive frequency components have annihilation operators, the negative frequency components have creation operators. So those are the phase-matched terms in the quantum description of this nonlinear optical process. What were classical complex amplitudes become quantum mechanical creation-annihilation operators, right? But so now we see what's going on from the point of view of the quantum mechanics. The three-wave mixing process is a process by which we, say, annihilate a pump photon and create pairs of photons in these phase-matched modes. Okay? And in particular, so in the non-depleted pump approximation, we take the mode, the pump, to be in a coherent state. And we take it to be constant, unchanged, right? In which case, we just replace this thing by the complex amplitude, okay? And thus what you see in this case is that my interaction Hamiltonian is going to be of the form some matrix for all the modes that are phase matched with some complex amplitudes that looks like this. Whereby I create or annihilate pairs of photons, and I'm ignoring any change to the pump because I'm taking the well-founded, non-depleted pump approximation. Now this Hamiltonian, you should recognize. This Hamiltonian you're studying in your homework right now, this is the generator of a two-mode squeeze state, right? In particular, if I started with the vacuum, we talked about the parametric amplifier, whereby I amplified, but I can also have what's called a parametric oscillator, whereby I don't inject anything into the signal of the either. And in particular, let's look at again the degenerate case. Take the, okay. Then what I have is a one-mode squeeze squeezing type. Okay, so in that case, I'll have something that looks like zeta A dagger squared minus or plus, what do we call it, kappa. Doesn't really matter. A squared. Which once again we recognize as the Hamiltonian that generates one-mode squeezing, right? And I could, in the laboratory, I might do this in the following way. In what's the workhorse of making squeeze light is what's known as an OPO, an optical parametric oscillator, as opposed to an amplifier. God knows what that means exactly. But anyway, the point here is that I might have a situation where I have a cavity that looks like this. Let's say I have a cavity whereby the pump is not resonant at all. It's completely transparent to omega 3. Let's say omega pump. However, I create this kind of bow tie-like thingy whereby this thing, let me see if I can draw it. Good luck to me. Looks like that. We're having output color. Okay, so this OPO is resonant for that frequency in this bow tie-like configuration, but it's completely transparent for the pump. Okay, and inside here, I place a Quadrature crystal. Okay, and I pump it. Then what will happen in this case is I start with the vacuum at time t equals 0. I have the vacuum for signal. And then the system evolves as a function of time according to this mode. And what will come out in that case of this port? If I start with vacuum and it evolves according to this Hamiltonian. A squeeze vacuum. That's how you make squeeze vacuum. You have to pump, you have to have an OPO. I mean, I don't know about all the alignment and the gain and all of that's a complicated story. But it's like a lasing. But it's a parametric lasing. Now, I can think about this just like the child on a swing or your little pendulum that you're pulling up and down. What's being done here is, I mean, this is a question I think you asked earlier, Matt. I talked about parametric resonance and how I can think about that as a change of the length of the cavity at twice the frequency. In this case, omega signal is equal to, so the pump here is at twice the frequency of the signal, right? Because they're phase matched. And so what I'm doing is I'm changing the optical path length through the change of the index of refraction that's being modulated at twice the frequency. So I'm not moving the mirror, I'm just changing the optical path length because the optical path length of the red light is affected by the blue light through the nonlinear mixing. So all I'm doing is basically effectively changing the length of my oscillator at twice the resonance frequency, and I get parametric amplification. And I parametrically amplify the vacuum fluctuations. So this picture over here would be exactly the same, but I would just think about that from this point of view is that the vacuum is a bunch of different phasors some distribution, and they get amplified in the OPO and come out, depending on the phase of the pump, squeeze. Very good. All right. Now, you may be thinking to yourself, what the hell is quantum mechanical about this at all? I mean, you did this classical nonlinear optics, and you just said this vector goes to that vector, and you had a statistical distribution of different initial classical phasors, and they each did their own thing. Fine, you want to make it fancy and put A's and A daggers in there. That you want to make it fancy, but who needed sticking quantum mechanics for any of this? It was just perfectly fine to think about classical nonlinear optics and phase-sensitive amplification, and that explained it all. Well, this is a very subtle point that we're coming to at the moment. And the question is what we mean by classical and what we mean by non-classical is a subtle business. So let me try to frame this a little bit more. So we have defined in the past, we said, well, let's look at operationally how we describe a particular measurement. So this is a very operational question. The question is, do I need a quantum mechanical theory to describe the measurement outcomes I see? Because at the end of the day, all that quantum mechanics and any physical theory should tell us is a prediction about what we will measure. Because that's what physics is. So the theory has to, if it doesn't do that, it's not physics. It could be something else, it could be string theory, but it's not physics, okay? So physics is about what we measure. And quantum mechanics is a particular theory that tells you how to predict the probability of measurement outcomes. And that theory is one that is incompatible with classical logic, which is the theory of probability. Probability is the language of logic. But if we can get away with classical logic and classical probability, then we would say that the phenomenon is essentially classical, because we didn't need a quantum mechanical theory of probability amplitudes and quantum interference to predict those measurement outcomes. Okay? Now, we looked at a specific question in the past. We said, in the Glauber theory, we considered coincidence counting a photon of square law detectors. Right? And so, you know, there was incident on each one of these guys, some field, and we looked at joint probabilities or joint rates of detection of this photon counting, right? And from the Glauber theory, that was related to normally ordered products of the intensity operator of the end detectors, right? So we would say the light was classical is if these kinds of expectation values were describable in terms of classical averages over classical probability distributions, right? So we would say that the light is classical if this is described by classical statistics. And the class of states, quantum states of light, for which that was true, was the set of states which we thought about as a statistical mixture of coherent states. When this Glauber P distribution was an honest-to-God probability distribution, then this thing, quantum mechanically, is just equal to the average over the probability distribution of the squares of the amplitudes, right? So what was a quantum mechanical operator now just becomes a statistical average. Okay? And we said that class of the states of the quantized electromagnetic field are classical. And squeeze states cannot be described this way. Squeeze states are not a statistical mixture of coherent states. We saw that, whether we remember that or not, earlier in the semester when we looked at the condition. Every sort of state of this sort will always have fluctuations in the quadratures that are at least as big as the vacuum. And squeezing has, in some directions, fluctuations below the vacuum level. So it can't be described. So in that sense, squeezing is non-classical. In the sense, if we try to do some direct photon counting, we're going to see sub-shot noise. We could see sub-Poissonian statistics, for example. Right? However, this is not the only measurement that we can do. Right? This measurement involved these direct photon detections, which was related to these normally ordered products, things like A1 dagger, A2 dagger, dot, 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 A1, A2, dot, dot, dot. That's what was with those guys as normally ordered products. But suppose instead of directly measuring, let's do homodyne detection. That's a different measurement. It's not direct photon counting. It's taking whatever the light we want to measure and mixing it on a beam splitter with a strong local oscillator. And then, you know, we could have a balanced homodyne if we like, because that's fun. And if this mode is A, what we measure here is X. The quadrature. So this measurement, the measurement outcomes don't depend on the number operator. They depend on the quadrature. Right? And so for example, let's just, for example, choose let's just set the phase to 0 for example. I'm measuring the quadrature x. Okay. Then suppose I wanted to look at what are the fluctuations on average, or x squared. This is this object. Right? But that object is not a normally ordered product. Something else. We got an A and A dagger in the wrong order if we're measuring that. This is not normally ordered. It's what we would say is this is symmetrically ordered. We have all permutations of A and A dagger in this particular thing. So the question, the relationship between statistical averages over the P representation and the quantum mechanical expectation value required normal ordering. Then those two go hand in hand. You can see, I take the expectation value of this, and then all the A's turn into alphas, all the A daggers turn into alpha stars. Normally ordered is where this came from. If we don't have normal ordering, then there's nothing we can't relate this expectation value to averages over the P representation. In fact, well, we could if we liked, and we like sometimes, to say, well, that's X, right? So I have the harmonic oscillator. If you wanted to write this expectation value in terms of an integral, how would you do it? This is the expectation value of the operator X. How do you calculate the expectation value of an operator that depends on X? Oh, thank you. Excellent. You have the wave function in the X representation. That's a perfectly good representation of our Fock basis. I mean, our Fock states, right? Our Fock-Hilbert space. I can have the X representation. So this would equal the integral over X, whatever the wave function is, squared dx. That's what that is. But now I ask you, for the specific case, let's say that I have squeezed vacuum. What is this? What is the probability distribution in quadrature space of a squeezed vacuum? It's a Gaussian. It's a Gaussian with whatever the width is, right? You just apply the Bogoliubov operator to that. You look in the X representation. This is going to be a Gaussian. We did that. So this itself is going to be equal to whatever the squeezed vacuum is, which will be, in this case, Now notice, this is an honest-to-God probability distribution. So, as I drew in these pictures somewhere, these guys, this was a perfectly good description of what was going on. There was a Gaussian distribution here, and it underwent some transformation. And I can treat it in terms of perfectly classical probability distribution because it is with respect to this observable. So, the moral of the story here is you can't talk about something being classical or non-classical unless you're asking with respect to what kind of measurement you're doing. Squeezed light is non-classical with respect to photon counting, but it's completely classical with respect to homodyne detection. And that's why we did that problem that you had, I don't know, with the first problem of this week's homework assignment, where we just had, a mechanical problem of an oscillator and we saw squeezing, because it's a purely classical phenomenon from the point of view of homodyne detection. Now this, I think, is a very deep and powerful newer insight that maybe you haven't thought about in the context of quantum mechanics. And we're going to now try to get into this more deeply for the next remainder of this lecture and probably all of next week in trying to think about representations in phase space and classical versus non-classical. So the motivating story up here is to say the squeeze state, when it represented in phase space as a P function, is going to be non-classical, meaning it's going to be negative or even highly singular. And it can't thus be described in terms of classical probabilities. And that's the appropriate representation when thinking about photon detection. On the other hand, the squeeze state, as we will see, will have a different phase space representation, which is known as the Wigner function. And that Wigner function is positive everywhere, which is to say that with respect to homodyne detection, and we will see that the Wigner function is the function that you should look at when thinking about homodyne detection, is everywhere positive, and therefore this is classical. Okay. All right, so how do we think about representations in phase space? I mean, the problem, why this is complicated, is that X and P don't commute. So there's no straightforward way to think about a phase space representation. There's no unique way of doing it. And we're going to see that's intimately related to this question of different observables that you might measure, which are incompatible, right? The number operator doesn't commute with the annihilation operator. So they're, or with the X operator. Those are incompatible observables, okay? So how would we try to think about a representation in phase space? Well, we have, of course, something which is kind of both x and p, right? We have coherent states. Now, coherent states are not eigenstates of a Hermitian observable, so they don't have the normal kind of completeness and orthonormality. In addition, this is in infinite dimensions, and there's all kinds of crazy things that can happen in infinite dimensional Hilbert spaces. Nonetheless, I don't remember if we showed this for homework or not, this represents what we call an overcomplete basis. So they're overcomplete because they're not orthogonal, right? These guys, if I look at the magnitude, they have an exponential overlap, right? But they are complete in the sense that I can look at this, and this forms a resolution of the identity. Right? We did that homework problem where this guy, in terms of Fock basis, you can prove that. So one thing you might say is, if I were to guess, I have the coherent states, I want to write down a phase space representation. Well, instead of the x basis, let's look at the coherent states, right? And think about these guys. You can think about that. That's a perfectly good representation. If it was a density matrix, I would generally write it like this. And if I wanted to be normalized over this whole thing, I would divide by pi, because of this factor of pi. Okay. So that's a perfectly good distribution I could think about. This one is an honest-to-God probability distribution everywhere, because it's always positive. It has a name. This is known as the Husimi representation, or the Q function. Husimi wrote this down first. In a completely different context outside of quantum optics, but it's a perfectly good representation. Now we have the Husimi distribution. That's a perfectly good probability distribution. We'd have to think about what kind of measurements that would be associated with. In fact, it is associated, for those of you who have some real background, you might recognize this as a positive operator value measure. Any resolution of the identity over positive operators is what we call a POVM. And this is a really good M because it's a measure over the space. It's a positive, it's an operator, it's a measure. It's a POVM. So if I can somehow measure this POVM, I would measure the Q function. That's another homework problem for the future. So now we have three different possible kinds of guys. We have this guy. This somehow is different from this because this could be negative. We have the Husimi, and we have the Wigner function, which I haven't even defined yet. All of these represent different phase space representations, and they're useful in terms of different measurements we would do. The P function in terms of direct detection, the Wigner function in terms of homodyne, the Q in terms of heterodyne. So, how are we going to deal with this? Well, the different representations have to do with the non-commutivity of x and p, or equivalently, the non-commutivity of A and A dagger. Okay. So let's say let's talk about different phase space representations. And the question of operator ordering. In other words, what order I put A and A dagger makes a difference because they don't commute. Let's say I have some operator which is a function of A and A dagger. Okay? For example, n squared. Okay. N squared is A dagger A times A dagger A. Now, I could do commutators to rewrite this and normally order it. Okay? So I could write this by commuting this as A dagger plus A dagger A. Right? Those two operators are equal. You agree? This operator, just to remind you, there's this confusion of this notation. This is the normally ordered, what I call normally ordered, the language gets a little bit complicated. Here, these two guys are exactly equal. This is not equal to this. This symbol with the colon on the end means close your eyes, forget about the fact that these guys are operators, just move all the A daggers on the left and all the A's on the right.
You're missing the square. On the n inside the normal order symbols.
Oh, yes, n squared, thank you. Thank you, yes. Okay. Okay, everyone clear the difference between those things? I could also anti-normally order this and put this equal to A with a little bit of work that I'm too lazy to do on the board. I think that's what it is. Let me look at my notes.
Do you need another dagger on that first one?
I do. But let me make sure. I don't really care what these numbers are, but let me just double check that I maybe did it right. If I did it right in my notes. Yeah. Okay. Thank you. All right. So these three operators are equal. Okay. Now suppose I want to define a function which is a representation of this operator in phase space. What I want to do is I want to set A to alpha and A dagger to alpha star. But there's three different functions that I would get depending upon how I moved around the A's and A daggers, right? So there are three different representations that correspond to three different operator orderings. And so I'm going to put a little symbol on the bottom sigma. Okay, not to be confused with alpha. I hope you can tell the difference between my sigmas and my alphas, which represents the ordering. So sigma equals +1 is going to be normally ordered. Sigma equals 0 is symmetrically ordered. And sigma equals -1 will be antinormally ordered. Okay? And then A sigma of alpha is going to be, I take the operator F, which is written in a particular order, and set them equal to one another. So for example, A0 here is this guy, that's a symmetric guy. That's going to be alpha to the 4th. The normally ordered guy is alpha to the 4th plus alpha squared. So I took this function where everything was written in the normal order and I substituted it. The anti-normally ordered guy is this guy. These are 3 different functions of the variable alpha, but they represent 3 different representations of the same operator. In the same way that we can have position representation, or momentum representation, or a Fock state representation, they're all different representations as we will develop the formalism for the same operator. And they have physical meaning in terms of their relation to measurements that we would do. Okay? Very good. So we're going to begin then, spend 15 minutes beginning to set up this problem. I hope you're sufficiently motivated why this is interesting. This is an unfortunate complicated mathematical mess. And I'll do my best to try to keep it straight for everybody, but it gets a little hairy. And I should have brought the reference. I will do that next time. But this was all laid out in the mid-1960s in the PhD thesis of none other than Professor Kevin Cahill, who was a student of Roy Converse. And so I'll link you to those papers. They're great papers. All right. So let's say I have this operator A. And I can always express it in a power series. So this thing is a function of A and A dagger, just like the one we had up there. This function can be written in a power series in ordered products of A and A dagger. Let me just make sure my notation is what I want here. Yeah, it is what I want. Okay, so what does this symbol mean? This is a sigma ordered product. Okay. So the normally ordered guy is just that, nothing else. Okay. The anti-normally ordered guy This is the other way around. I move all the A's to the left, all the A daggers to the right, forgetting about the commutation relation. So this symbol with the -1 on the bottom would mean this. It means close your eyes, forget about commutators, move all the A daggers to the right, all the A's to the left. Okay. The sigma 0 case is the sum over all permutations. I'm going to write that. I always don't know how to write this formally. So I pick m out of n plus n, that's my combinatoric factor, and then I sum over all permutations of that, ignoring the commutators. So I'm looking at all possible permutations of these operators, ignoring their commutators, add them all up. The number of them is this, and I just divide by that. Okay? That's the symmetrically ordered product. Okay? Now, these coefficients in the power series are going to be different depending upon what ordering. We already saw that up here, right? In this case, there's a coefficient where n equals 2 and n equals 2. That's the same coefficient here, but there's also a coefficient when n equals 1 and n equals 1, right? In that sum. And this guy has a different coefficient in that power series expansion. In this power series expansion, that coefficient is -3, and it also has a coefficient in the power series expansion where n and m are equal to 0. So what these coefficients are depends on the ordering. But in all cases, the sum adds up to the same operator. Is that clear? Just like that did. Cool. And voila, we have the answer now. So the sigma ordered representation is just this power series where I set a dagger to alpha star and A to alpha. At that point, they all commute. That's just a number. But it's a different power series because it's a different set of coefficients. Okay. So our goal is to find these sigma ordered power series. If we can do that, we're done. We're golden. Because then we just have to plug in, just substitute wherever's on a dagger, an alpha star, an A, and alpha, and sum it up. And we have the representation. Okay. All right. Now I should warn you, I was thinking about, the notation that I use is not, there's some funny minus signs that go on in the way the literature is defined. To me, this is the natural way to define it. It's not the way Cahill did it. There's a minus sign opposite, so I warn you, I'm sorry. I'm sorry the world happened to you, but you're just going to have to live with me. This is our convention. Okay, I just warn you. Yes, sir?
So the operator takes form of A. Is the sum also with sigma? Or are you choosing?
I'm choosing a sigma.
Okay.
So this is for a given sigma, right? So, as I said, we did this process by hand here. In this case, sigma equals 0. This guy is the symmetrically ordered version of that. This guy was for sigma equals +1. That's to say we by hand moved the A's and A daggers around in order to see what the coefficients were. And for each of these sets of coefficients, we had 3 different functions, right?
So the coefficients, when you move to this outer,
These coefficients?
yeah, they stay the same, right?
They're the same, exactly. They're the same. That's your whole goal, is to find out what these coefficients are. Once you have them, you can do the power series. Now, we're not going to do that sum. There's going to be a much trickier way, but conceptually, that's what's going on. If you can do this, if you can find these coefficients by hook or by crook, then you have the representation, because that's what defines it. Okay, let's go to a fresh board for a fresh idea. So, the mathematical trick that will allow us to do that is to make use of a generating function, which is not too surprising why this is the right generating functions to think about. The star of our show is going to be the displacement operator. So let us remember the displacement operator, phase-space displacement operator, which was this, right? Which, written in terms of x and p, is that, right? So that's an interesting thing. You notice this is like a operator. This is going to be a very hand-wavy term, an operator plane wave in phase space. It's plane wavy. It's got operators. It's got x's and p's.
Makes sense, at least, right?
Yeah. So that we know that plane waves are kind of a good basis for functions. The displacement operators are a good basis of operators for operators. We can have a space of operators. And this is a basis for the space of operators. Okay? It's what, if we really want to be fancy, we would call this set an operator frame. A frame is just a fancy name for an overcomplete basis. Now, this is something you may or may not, depending on what you study. What does it mean to be a basis of operators, right? Matrices themselves are a vector space. The set of matrices form a base is a vector space. And we can expand matrices in terms of sum of other matrices, which are a basis of those matrices. So let me just remind you. Let's say I have a D by D matrix. This is a D squared dimensional vector space. One way I could do it is just stack all the columns together and I have one giant vector. That would be one way of looking at it, why there's an isomorphism between matrices and vectors. I don't have to do that. I could just think, let's use our favorite Dirac notation. I can write M as so that's a matrix, right? These I'll call the basis of matrices. There are d squared of these, and I just take a linear combination of them. So these things form a basis of a matrix. That's the standard basis, if you like. Okay? And I can have an inner product. Borrowing from the Euclidean inner product, if I stack the matrices, it would be equivalent if I have 2, and now I'll use curvy for my, this is now, in a super vector space, I'll call this thing M is equal to the sum So now this is a vector in my bigger vector space. Is that clear? With curve instead of, now this represents kets. I don't know why I'm doing this, but I'm doing it because I've turned my matrices into vectors in a big vector space that has this dimension. And those vectors are kets of their own flavor with curvy kets. Okay? this is just rewriting this as a vector space. And now I can have an inner product between n and m, which would be given by this, all that sum would be that it's equal to the trace of n dagger. That's what's known as the Hilbert-Schmidt inner product. But you know, I hate using these names because who cares? I have to remember what it is. It's, you know, you just have to, that just impresses your friends that there's some fancy name associated with it that has somebody, it's the inner product. It's the Euclidean inner product. Okay? All right, so with that said, the set of displacement operators forms a basis of the space of operators on the Fock space. Now, there's a lot more subtlety in this because this is in infinite dimensions. And what kind of operators are we talking about? Are they bounded operators? Are they unbounded operators? There's mathematical subtleties when you have infinite dimensions. I'm going to ignore them because I'm good at ignoring mathematical rigor. But, you know, Cahill did it right. So what is the point I'm trying to say here? So these guys, firstly, they're orthogonal. If I look at the inner product between two of these guys, and using the completeness relation we had about the coherent states, I could always calculate that. And I don't remember whether I had to do this from a look or not. I should have if I didn't. This is one of the... That's how you take the trace. You sum all the diagonal matrix elements, in this case in the coherent state basis, is equal to, there's no 2 in there, pi, a delta function in 2D, alpha minus beta. So they're orthogonal, as plane waves are, and they're complete. They're complete in the sense that I can think about them as a basis. So I can take any operator, I can project it onto that guy, and then sum it up over all space. Okay? So I took the operator, I projected it onto that basis direction, and I add the basis and I add them up. It's pretty crazy notation. But this is just like saying V is equal to the sum over all the basis vectors. I project the vector onto the direction, that gives me the coefficient, I add that up, that's the vector. That's the same thing. We have this incredible abstraction here. And this, of course, is equal to the trace of D dagger with A. Now, why do we go this way? Well, the reason is that we are able to easily look at operator-ordered products of this, right? We already looked at normally ordered and anti-normally ordered using Baker-Campbell-Hausdorff. And so we were able to use simple relations to re-express our operator-ordered power series in terms of integrals of this kind. And they will ultimately, after a bunch of math that will drive us crazy with minus signs, come out to something which I hope will have some physical intuition about what we're talking about, what these things mean. Okay? But we have a little more work to do.